Well, welcome back to part 2 of our Statistical Process Control Clinic. If you recall where we left off, in part 1 we were talking about frequency distributions and histograms. And you'll recognize that those are sort of static objects. They're a static view of the data. And in part 2 we're going to be talking about more of a dynamic situation where we're going to be measuring and recording data in sequences of operation over time, and it gives sort of a live look to frequency distributions. Well, we'll go ahead and start with an exercise, and this exercise is not original. I took it from Grant and Leavenworth's description of Shewhart's chip bowl experiments, in which Walter Shewhart developed this whole process and these tools called Statistical Process Control. And it starts where he started with 997 numbered chips, which represent, think of them as a constant process stream. And our objective in this exercise is to describe and quantify the two process parameters without 100% inspection. Well, 997, that's an awful lot of them, but there could be 9,000, 900,000, 9 million. So the idea is sampling from a process and taking that sample and applying something about the population and doing something with that. What we're going to be doing is determining if that process is stable and determining if that variation represents random or special cause variation. So our plan is to sample 25 subgroups of 5 chips, record the data on a control chart, plot the points, determine and draw the control limits, estimate the center and the width of the distribution, and then from that data, if the process is stable, describe what that population looks like based on a sample. In constructing our control chart, we're going to be using some old school techniques so that you have an appreciation of what's going on. I know that in current day, most statistical process control work is done on a production floor using maybe automated gauges, which feed into computer software that does all the work for you. But I think it's important for us to have an appreciation of the old school so that you can do it by hand. Also, if you're interested in getting into this without setting up the computers and the automated gauges, you know that you can get into this for almost nothing. You have a piece of paper in front of you and some pencils and a ruler and some markers, as I'll show you in a few minutes. Control chart, this is commercially created paper, nothing too special about it. Up on the top is some information you might collect and record about what process or products you're measuring. What you have is 2 charts. The top chart is the average chart, which speaks to the center of the distribution. And the bottom chart is the range chart, which speaks about the width of the distribution. Beyond that, on the very lower part of the chart is where we collect the data. We're going to be using some formulas, control limits for averages, control limits for ranges, and for the estimate of the standard deviation. You can look at this information again. It's in the statistical books, and we're going to be using it in our calculations in a few minutes. Also, we're going to be referring to this table. This table is provided by the ASTM, and got the lines crossed there. Again, we're going to be using a subgroup of 5, so a horizontal line there identifying N5 in the subgroups. We're going to be using it for the A2 factor 0.577, 2.326 for the small D2 factor, and for charts for the ranges D4 2.114, again from the ASTM. In order for you to see how a statistical process control chart is developed, you need a process and a few simple tools. On the left, we have a process very similar to the Shewhart chip bowls described in Grant and Leavenworth's text. In this case, we have 997 chips, each one with a numeral applied, and this is going to simulate an unknown process, a process making products, and the parameter that we're going to be measuring are the ones described on these chips. In addition to that, you have the SPC chart that we described in a previous slide, and some pretty simple tools, a couple of Sharpies, a ruler, a pen, and a calculator. So in a normal live class, I have classroom participants help me select the samples. The students will be recording the data on their control charts, and then we'll go through the process of doing the calculations live, and then plotting the points, connecting the dots, calculating the control limits, and then assessing what the distribution of individuals is from the selection of samples. In our recorded class, I'll be doing this on my own, and I'll bring you back when the data is recorded, and I'll take you through the sequence of calculations so you can get the whole concept. So the steps of setting up our first statistical process control chart on this process are pretty straightforward. We have our SPC bucket, which has the process chips in it. And again, this is like a machine or a process producing parts. And the numerals on each one of the chips represent some kind of process parameter or process characteristic that we're interested in measuring to see if it's in control and it's staying in control. We have our few tools, markers and a pen, ruler, and a calculator. And so what we'll be doing is data collection, and typically in production you'll have these rows filled out, the date and the time, and you'll be putting in for example, in the time, the frequency of when the checks were made. Maybe they'll be made every hour, every half hour, or 15 minutes, depending on how often you think the process will change. And then we're going to be selecting 5 samples per subgroup. Each one of these columns represents a subgroup. Now, the number 5 is nothing sacred. We'll talk about this in another one of our practical problem-solving modules. We'll be talking about rational subgroups. But a subgroup of 5 is, in this case, very cheap to take, and it's fairly quick. So we're going to use 5. We'll talk about why we're doing that maybe in another, like I say, in another module. Then later on, after we collect all the subgroups, we're going to develop a sum, an average, and then a range. And the range, of course, is the difference between the largest value and the smallest value within each subgroup. And different operators might put their notes, their initials here, and perhaps even a part number here, so that if there is different parts run on the same setup, you'll be able to detect any changes that we make. After that's all done, we'll be plotting the points and then connecting the dots and calculating the control limits as we go along. But before we start, so we're going to just start the process, and I'll go through a couple of subgroups with you, and then we'll come back and show the completed chart. So I'm tossing these chips around a bit because we want to make sure that each selection is random in nature. That is, each chip has the same probability of being selected as others. So first one is a 43. So in subgroup number 1, $27. 30. $29. $28. Second subgroup is 39. $35. $45. $22. $37. So I'll continue on like that and pick up all the different subgroups here, 25 subgroups, and bring you back when that's done. So what we have here is just a table representing the data that was collected in the sampling for the control chart. Across the top in yellow, you can see that we had 25 subgroups. Each subgroup has 5 parts or 5 chips that were selected. For example, in column 1, subgroup 1, 43, 27, 30, 29, and 28 add up to 157 divided by 5, subgroup average 31.4. And then the range, of course, is the difference within the subgroup of the largest value minus the smallest value. So if you go across and add up each one of the subgroup averages and divide by 25, it's called the grand average. It's the average of the averages, and that is 30.6. And if you add up all the ranges and divide by 25, it's 25 becomes 25.5. That's the average range. We'll be using those numbers in our further calculations of the control limits and our estimates of the process standard deviation. So at this point of the process, we've done a little work. We've collected the data in subgroups of 5. We've done 25 subgroups. We've calculated the average, the subgroup average of each, added them all up in each subgroup, divided by 5, and you get an average. And you look at the dispersion, you look at the largest number, and then you look at the smallest number, you subtract the smallest from the largest, and you get the range. The difference between the largest value and the smallest value in the subgroup is the range. So then we've done that already, and you'll see the calculations on one of your slides coming up. You can do it with a calculator like I've done, or with Excel, whichever is easier. You want to make a note of this information on the control chart. So in our case, with this data, the grand average, or the average of the averages, is 30.6. So we put that right up here where it says X double bar. And the average range, that is the average of all the ranges, is 25.5. And I'll go through that calculation right now. We're also going to be using some factors from that table, that ASTM table, that will be in your slide pack as well. But before that, we'll want to scale the chart, and we can start make the scale such that it does use up a good part of the control chart. You don't want it to be the averages you're plotting be beyond the scale of the chart. Doesn't make sense, and you don't want to make it so small so that you miss any fine detail. And so in this case, I'm going to scale the chart, the average chart, in units of 2, so 30, 40, 50, 60, 20, 10, and 0. It doesn't work out exactly that easy on the range chart. We'll do 0, and we'll do those in increments of 3, 15, 30, 45, and 60. And again, we'll use the numbers that we've calculated already. The average range is 25.5. We'll put that in here. And the grand average, which I'll show you how to calculate in a minute again, is 30.6. So let's get to those calculations. Pretty straightforward. So the first number that we want to calculate is the grand average. And the grand average is, looks like that, the X double bar. And that is the average of all the subgroup averages. So X bar 1 plus X bar 2 plus X bar 3 all the way to X bar 25, since we have 25 subgroup, divided by 25. And if you go through the numbers, you'll find that in our case it is 30.6. And our average range, and that is the R bar, which is the sum of the average of all the ranges, so that's R1 plus R2 plus R3 all the way to R25, divided by 25. That average range, as we've mentioned, is 25.5. So what we'll want to do here, just for graphical purposes, we've got our average, grand average, and our average range. Why don't we just plot that on the chart, find 30.6 on this chart, and draw a horizontal line there. And that's right about here. And the average range is 25.5. So that's 15, 18, 24, roughly around there. Next thing we'll want to do is calculate the upper and lower control limits. So the formula for the upper control limits and lower control limits also found in your slide pack. The upper control limit, or the UCL for X bar, is the formula X double bar, the grand average, plus something called A2, again that's in your chart, times R bar. In our case, the A2 number for a subgroup of 5 is 0.577. So our calculation is 30.6, which is the X double bar, plus 0.577 times the average range, which is 25.5. And that number works out to be 45.31. So that's the upper control limit, X bar. So these you'll find are symmetrical about the mean. So the lower control limit, X bar, is the X double bar minus A2 times R bar, or 30.6 minus 0.5777 times 25.5, which is 15.9. So that's the lower control limit, X bar. So why don't we find those numbers? And we're going to get real fancy here. We'll put those in red. So the upper control limit for X bar is 45.31. Won't be able to find that last digit there. It's about 40, between 40 and 50, so that's about 45 right there. And the lower control limit is 15.9. It's almost 16. So you can see that is symmetrical about the average x double bar. And the again, our average range is 25.5 in the upper control limit. So we're going to calculate the upper control limit for the range now, and the lower control limit for the range. So the formula for the upper control limit for the range is D4, again, that's found in your chart, times R bar. Again, that's a function of a subgroup of 5. So that's D4 is 2.114 times the average range. Average range is 25.5. So the upper control limit for our range here is 53.9. The lower control limit for the range is D3 times R bar. Got to put the designation there. And you can see that D3 for a subgroup of 5 is undefined. So we'll call this undefined. So let's find 53.9 on our chart. 45, that's 60. 53.9 is right around 54, roughly there. So these are our control limits. What we're saying with our control limits is if our process is stable, that is in control, all the subgroup averages will fall within the boundaries of the upper and lower control limits on the average, and below the upper control limit on the range. And there are going to be some special circumstances and rules that we'll get to in a few minutes, but that's a general rule at this point. So next thing I'm going to do when I bring you back is I'm going to plot the points and connect the lines, and we'll see how we did on our control chart. Bring it right back. Okay, so we've progressed in plotting all the points. So you'll notice on an SPC chart, the increments that we're plotting are not so exact in that, for example, this is 31.4, and the scale here is broken into twos, so it's 30, 32, 34, 36, 38, 40, so it's right about here. It's impossible to find exactly 31.4, so you'll put a dot that's very close to what you think that might be. And the same thing on the range chart. The average range for subgroup number 1 is 16, so it's a bit more than 15. So I plotted the points, so now we're going to just connect the dots. And in production, you'd be doing this every time you'd have a subgroup. So you wouldn't be doing this all at once, you'd be doing this as you go along. And you see it's not too much of a burden. It's simply selecting the samples, adding 5 numbers up, calculating the average, determining the range, plotting the point. This is how it was done back in the day, if you will. Now that there are lots of software programs connected to PCs and measuring instruments that do it automatically, but I wanted you to see how straightforward it is, easy to do without a computer. The expense to start doing this program is pretty much zero. So what we've done here is plotted our points. You can see that all the points on the average chart fall within the control limits, and all the points on the range chart fall within the control limits. So we can say at this point the process seems to be stable, and so we now can go to our next calculation, and that is the estimate of, again, these are, since these are samples, the estimate of the standard deviation. Estimate of standard deviation, and that term is a sigma, and since it's of a sample, we put a little hat on there, that's just some designation, is R bar divided by small d2. Again, you'll find that in the table. So our R bar right here was 25.5, And the factor D2 for a subgroup of 5 is 2.326. So our estimate of our standard deviation turns out to be 10.96, roughly 11. So what we're saying by that is that we have a process that is stable, it's in control, that is, that it's repeatable, and we think the process has a center roughly at 30.6, we'll call that 31, and has a standard deviation, because that's the X double bar, and it has a standard deviation of roughly 11. So as we talked about earlier, so if we talk about a normal curve with, these are all 11, so let's just use a little bit of our calculator. 31 plus 11 is 42. 42 plus 11 is 53. Plus 11 is 64. 31 minus 11 is 20. Minus 11 is 9. Minus 11 is minus 2. So we think that we have a distribution that is centered right around 31, has a standard deviation of 11. So we think if we can probably draw our graph. It sort of looks like that. And that's what our distribution we think is going to be. So this will be our estimate. And if so, in a very short order, we can tell our process is in control, and we can make an estimate of what our frequency distribution looks like. Now, so what does this tell us about, what are our specifications? Well, I don't know what our specifications might be in this process. If, let's just say it's, I'll make up some numbers. Let's just say it's 30 plus or minus 10. So it'd be about 40, right? So anything beyond here would be out of specifications. We got a lot of trouble. But on the other hand, if it was 30 plus or minus 100, then we're in really good shape. So this information doesn't necessarily inform us about whether these adhere to the specifications. The specifications are drawn by engineers, and they have something to do with the fit and function of the process, the product in the world. This simply tells us what the process looks like. And so what we've done here in just a few minutes is we've selected samples from the SPC bucket, which simulated the process. We created 25 subgroups of 5. We've calculated each subgroup average. We've calculated each subgroup range. We've scaled our chart. We've calculated the X double bar, the grand average, and we've calculated the upper and lower control limits for the averages. We've calculated the average range, and we calculated the upper control limit for the average range, and then we went ahead and made an estimate of our standard deviation. Good work. So our estimate of the process center and standard deviation was shown at 31 and 11. The actual average of that distribution was 30, and the standard deviation is actually 10. So we made a pretty good estimate of what that process looks like. So beyond the average and range chart, there are other types of variables control charts. As we talked about, the average chart speaks about the distribution level. The range chart speaks about the distribution width. But beyond that, there's something called a medians chart, and that helps us calculate the the center and width just in a little bit different way. Since the median is a value in the middle, let's say you have an odd number, 5 data points, if you rank them top to bottom or bottom to top, doesn't matter. The value in the middle is the median, and you can plot the median. You recall there's a mean, median, and mode. The mean is the arithmetic average. The median is the value in the middle, and the mode is the value that occurs most often. And beyond that, the average chart, range chart, medians chart, if you have lots of data and if you have the use of a calculator or a computer, you can calculate standard deviation. For example, you've taken a subgroup of 50 or 100, which is maybe automatically or taken and samples selected, then you're probably going to have the advantage of having a computer calculate the standard deviation. It's an even better way to calculate the width of the distribution than the range. So before we go on, we've had a lot. Let's talk about a bit of a review. We'll start with variation. Variation is that expected part of everything in life and nature, and everything that we see has variation. We can describe the variation in a static way using a frequency distribution or a histogram. And we know that the individuals and averages tend to group themselves around some central value with some spread of variation. And we can describe that variation, the center and width, by plotting it on a frequency distribution or a histogram. Describing distributions, we often are most concerned with 2 process parameters, the center of the distribution and the width of the distribution. And with the use of statistical tools, allow us to determine if that variation is common cause and special cause with a control chart. Assuming the normal or bell-shaped distribution, the distribution of individuals and the distribution of averages will have the same center, but with different widths, consistent with the central limit theorem. The average and range chart, just as we've seen a few minutes ago, provide a method to plot and describe that process and product variation over time. We also know if the causes of the variation do not significantly change, that is, if the process has not changed, over time that distribution will exhibit certain and stable characteristics. On the other hand, if it does change, we'll be able to see that special cause and take action. If that process is stable, and in statistical tools, those calculations allow us to estimate the distribution of individuals without 100% inspection. So, now that you're adept at creating control charts, what is the chart telling us? Think about the process screaming data at us. It's got the information. We collect the information using gauges. We plot it down on a piece of paper. We now give ourselves a graph. We can see what that story is telling us. And here is a way for us to talk about what that graph is telling us that the machine is doing. 3 major rules that I want you to think about in terms of identification of out of control conditions. Point 1, easy one, most people just think about 1, and that is point beyond a control limit. 2, more subtle, non-randomness and stratification. Recall back to that graph where we showed the normal distribution and plus or minus 1 standard deviation from the center contains 68% of the individuals or averages. Plus or minus 2 standard deviations, 95% of the individuals or averages, and 99.73% of the individuals or averages were contained within plus or minus 3 standard deviations of the center. So therefore, when you think about that distribution of averages, you got to think of, well, you would expect to see 68% or roughly 2/3 of the points within the middle third of the SPC graph, and the other third on the outside of that 2/3 of the center. If you don't, we call that non-randomness and stratification. Also, shifts and trends. So things change, materials change, setup changes, maybe process parameters change. For example, air pressure or hydraulic pressure changes, and we're going to see perhaps a shift in the process. A shift is where the center line of the distribution changes. And we're going to detect that by 7 points in a row on one side or the other, or a trend where 7 points in a row which either ascend or descend. Now, control charts are not infallible. Errors are made. Since we're talking about a distribution of normal distribution plus or minus 3 standard deviations, it's 99.73. That really means that every time you plot a point and maybe you make a decision on that point, 3 times out of 10,000, it's going to be wrong. Now, that's a pretty low error rate, and so what we say is we take action on those out of control points because it's likely the error 3 out of 10,000 is very, very small. So when you're looking at control charts, think of the two charts, the average chart and the range chart, telling us two different stories. Primarily, the average chart, the top chart, is going to be talking about the center of the distribution and is it moving up and down, getting higher or lower, shifting, if you recall our work with the quincunx, left or right. Whereas the range chart speaks about variability. Variability improvement would mean that the points on a range chart are getting smaller and smaller and smaller. That would be great. But on the other hand, if you can see a trend or a shift on the range chart where the points get larger and larger and larger, that means quality has deteriorated and gotten worse. So the control charts really tell us two different stories: top chart, level control; bottom chart, with control. So as you recall, a core underlying tenet of the use of statistical process control is the central limit theorem. And the central limit theorem says that sample averages form normal distributions. And that's very useful because we know how the normal distribution operates. That is, plus or minus 1 standard deviation from the center contains 68% of the area, 95%. Underneath the curve is plus or minus 2 standard deviations, plus or minus 3 standard deviation contains 99.73% of the area or the individuals. So then when you take that concept of the bell-shaped curve and the central limit theorem and stand it on its edge, then you can see how that's applied to a SPC control chart, where the upper and lower control limits represent 99.73% of the area, plus or minus 2 standard deviations of the averages are 95%, and plus or minus 1 standard deviation of the average, 68%. Again, the sequence of slides that we're going to see coming up are straight from the Western Electric handbook, the Western Electric book that I spoke about, that you'll see in terms of a reference at the end of this presentation. It was written and published in 1951. So this is not new technology. It is tried and true. Western Electric was a company that was making telephones, and they wanted to have reliable telephones and switching systems. So they were using statistical process control to continually improve and control their variation. So here's a graph that you might consider normal variation when you're looking at a control chart. What you see there is a shift up. The center of the distribution has moved up pretty clearly. And there's a shift down followed by a trend. A trend might be the result of worn tools or something that's changing gradually, whereas a shift is something that's sudden. So again, back to a shift. On the left, you see the points pretty much in the center of the distribution. All of a sudden, boom, those parts have gotten bigger. Something has occurred. That's just non-normal. That's a special cause. And again, a trend up and a trend down, that's certainly not normal. That's a special cause. So remember, we talked about common causes. That's the normal variation. These things identify special causes. And that's when you want to take action. Stratification or non-randomness. Notice in this graph, almost all the points are near the control limits, and we'll describe what causes something like this to happen, but certainly that is a special cause. Now, how about this graph where literally all of the points are right near the center line? That's not normal. We would expect to see, as we did in our homemade control chart, selecting parts from that bucket, we saw random variation throughout the control chart. Here's something that doesn't look normal and is a special cause. So again, 3 things you want to use as sort of a rule of thumb. Okay, 3 thumbs if you have. Points beyond the control limits, non-random stratification, and non-randomness is stratification, and shifts and trends. Keep that in mind as we go along here. So again, natural pattern. Normal, here we got in the subgroup, whatever, number 3, you got a point beyond the control limit. Address it, fix the process, reset it, and go along. Pretty normal. So what's going on in this chart is certainly special cause variation. Here on the left-hand side, you can see the points are well beyond the control limit on the top. Then perhaps what you saw, perhaps C is a trend in the middle, and then certainly a shift below. So these are non-random, non-common cause data that's being presented, and certainly that's special cause, and you want to take action on that. So freaks, what that means is they're well beyond the control limits. Now it might be data collection errors, something like that, because all the rest of the data seems pretty normal. Again, beyond the control limits, you need to stop the process, try to understand what's going on. Interesting, something called cycles. You can see small groups, high, low, high, low, high, low, high, low. Perhaps something to do with a machine control like air pressure, hydraulic pressure. Perhaps it's operator involvement. First shift likes to run it here, second shift likes to run it here, something like that. But certainly some kind of cycle. Maybe your process is tied to an air compressor, and that air compressor doesn't go through, maybe you're not building pressure in an accumulation tank, which smooths out the air to running the machines. Something like that. Whatever it is, that variation is certainly not normal. It's a special cause, not common cause. Systematic variables, very, very predictable, very predictable pattern. Low always follows a high. What could that be? Oftentimes we call this over control. A new operator sees a point like you see on the very first one, very, very high. Oh my goodness, this is very bad. Shuts the machine down, makes a change. Second check, very low. Oh my goodness, it's too low. Shuts the machine down, makes a change, and it's like a dog chasing its tail. Over control, too much hands-on. Back to stratification here. All of a sudden, you see all the points within the first confines of the control limits. Let's just say, let's be kind here and say the process has somehow changed and improved. Great. Then when you see something like that, the action there is to recalculate the control limits and make them more representative of the data. If you see a process like this and it's not, there's something that's not been, this error has not been addressed, well, you know, that's really uninformed management. The process is running, quotes, too good. Unstable forms of mixture, again, tight patterns, tight data, but run at wildly different levels. This, you think that has this process has a great opportunity to be very, very high quality, because you can see like those first 4 points, those second 4 points, they're made in very, very tight patterns, but so they have a potential of being great quality, but since they're run at such wildly different levels, the overall quality is poor. Sudden shift in level, so recognizable pattern. This is really, really easy to see. Something has changed, materials changed, some kind of supplier has changed, a machine control has changed, all of a sudden, in this case, the parts have all gotten smaller than they should be, or smaller than they have been. Straight line. So what's happening here is that the data measuring system is not fine enough. You need to think about something called the 10-to-1 rule, and that is the smallest increment of measure should be no larger than 10% of the specification width. For example, let's just say you have a specification that's something plus or minus a half an inch. So the width of the specification is 1 inch. The roughest that the measurement instrument should provide you a measurement should be 1/10 of an inch. If it's smaller than 1/10 of an inch, that's great, but it shouldn't be any worse than 1/10 of an inch because that's 1/10 of the specification width. 10-to-1 rule, the smallest increment of measure should be no larger than 10% of the specification width. In this case, the operators can't discriminate between a 6 or an 8 or a 4 because they don't have a good enough gauge. Points on the control limits. This is pretty clear. I call it fear. You can see there's a trend going on, point whatever that is on the right-hand side. You're about ready to go out of control, beyond the control limits, and all of a sudden, 3 points just on the one side of the control limits. Operator certainly doesn't want to have the foreman down his back, so he plots it just within the control limit so he doesn't have to shut down the process. Call it fear. Under foreign management, operators trying to do a good job, clearly they can't. Instability, many things going on here, but clearly this is non-random special cause variation that you need to recognize. Grouping or bunching, very, very large fluctuations that's followed by very tight fluctuations. Again, many things going on here, different materials, different crews, but the potential for the process is right there. The money side is on the right-hand side. It looks great. That's the kind of process that we want to control, but we have to identify that portion on the left-hand side, certainly non-random. It's certainly special cause variation that you need to take action on. So, 3 rules that you might want to use for identification of out of control condition. First, points beyond the control limits. That's the rule that everybody sees in control charts and thinks that's the only one. Second, more sophisticated non-random stratification and shifts and trends. Summary. So back to part 1, quality is best defined as minimized variation around targeted process streams. This is what we want to produce. This is what we want to consume as consumer. SPC, Statistical Process Control, is a tool that provides us that opportunity to describe the data that's coming out of those processes and plot it, use it for minimized process and product control on the target. Use of those tools can and will result in an improvement of our competitive position. That is, we can reduce costs, reduce waste, make a better product, better reputation for our sales team, better reputation for the company. Statistical tools allow us to know more about our production process because we will be investigating those out of control conditions, will allow us to isolate and eliminate that excessive variation on-centered, right on the nominal. It's in our best interest as lean leaders, because I see statistical process control as a way for us to reduce waste, as lean leaders to simultaneously improve quality, reduce costs, and increase the capability of our employees. So thank you for hanging with me on that. We're going to now move in from variables into attributes. So variables versus attributes. We talked about variables as you're using a micrometer, you're using a caliper, you're using a depth gauge, you're using a scale. Attributes, good, bad, pass, fail, conductive, not conductive. It is much less sensitive to changes, but it's cheaper data to collect. We're going to use some nomenclature and some formulas for what we're going to call fraction defective or something called p-charts. N is the sample size. P bar is the total number rejected versus the total number inspected. And we're going to use these formulas, the upper and lower control limits, in the subsequent slides. Example of a performance chart, which we'll go through an example of. It is one big graph. On the top is, of course, the part number and the operation and so forth. On the left-hand side, it will be the scale that you want to use. And we call it a p-chart. People talk about it as a percentage chart. It's really fraction defective. That is what we're going to be calculating. And on the bottom is some data collection. Here's an example of a completed p-chart with sample size of 10. You can see the data collection on the bottom and the how easy it is to calculate the fraction defective. This has an upper and lower control limit, and an upper control limit and an average of fraction defective, the UCL, as you can see on the left, and the p-bar. And on the bottom, for practice, you can go through this calculation here of what the p-bar is, and then you go through the formulas. Now, you get what you pay for. Sample size 10, the upper control limit is pretty high. Think of the upper control limit as sort of a seat belt. It's going to save you from an accident. So the tighter the control limit, the more protection you have. In this case, only 10 samples. It's better than nothing, but not very much protection, as compared to the same exact data, but with a sample size of 50. Notice the upper control limit has come down, more protection, same process, more protection. So you're going to find out earlier if the process is unstable by taking a larger sample size. Again, on the bottom, for your practice, you can go through the data collection and the calculations yourself. At this point in our study of statistical process control, we're going to move away from the study of variables measurements and move into the study of attributes. Attributes oftentimes are characterized as good, bad, pass, fail, but they also could be considered maybe a component or a percentage of a mixture that you're trying to maintain. Point is, these are attributes, and here is a way for us to study how to identify out-of-control conditions and keep process in control. What you see in front of you is a bead box produced by the Lightning Calculator Company of Troy, Michigan. And you can see that, if you can see the fine print there, it has 2,600 beads. 1,800 of them are white, there's 400 red, 100 yellow, 100 green, 100 black, and 100 blue. And you can sample with the sampling paddles that they've provided. The first sampling paddle has 25. The second sampling paddle uses a sample of 50. And then a third sampling paddle is one for 100. I'm sure that if you wanted to change the sampling routine, you could change these up and make your own if you wish. So if you consider a process that's ongoing and you want to maintain the same fraction defective or the same percentage of a particular product characteristic, or perhaps if you're counting defects in your process, you want to maintain a certain level in that you don't want them to exceed a certain number, or perhaps maybe you're measuring a supplier's performance and you know their performance is guaranteed to some certain level of, let's just say, a characteristic, and you want to make sure that you're getting your money's worth. P-charts or performance charts is a way to do that. And there are several types. We're going to be talking about the most common one, the P-chart. So in a few minutes, we're going to be moving to a control chart. And here is an example of our performance chart. And guess what? We're going to be sampling subgroups. We're going to take 20 subgroups, and we're going to calculate in this case, we're going to call the red's defectives, all the rest of them are good. And we're going to see if our sampling process or sampling protocol can predict what the actual population is. So we're going to start that in a few minutes. So we're ready to start our sampling process, and perhaps we ought to mark up our chart to give it a bit of identification. So we're going to be calling this chart beads, maybe. And we're looking for red beads. And we're going to be taking a sample of 50 pieces. So n equals 50, sample size equals 50. So I'm going to take a couple of subgroups here. Please excuse the noise. And make sure our sampling paddle, all the holes are full. So in our first subgroup, we had 1, 2, 3, 4, 5, 6, 7, 8. 2, 3, 4, 5, 6, 7, 8. 8 red beads. We'll call these 8 defectives. And 8 divided by 50 should equal 0.16. Now you note that this is called a performance chart, and oftentimes people think of this as percentage, but we're actually going to be calculating and plotting fraction defective. Take another subgroup. In our second subgroup, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Twelve divided by 50 should be 0.24. Let's just check that. Yep, 0.24. Well, I'll come back in a few minutes and have all these prepared for you to look at, and then we'll do the plotting and calculating of the control limits. So here is the data that came out of our sampling of the bead box. In the yellow, 20 subgroups, and just below that in the gray, the data for each subgroup as recorded. We had 8 defective in the first subgroup, 0.16 was a fraction defective, 12 in the second, 0.24. If we add up all the number of defectives, it's 141, and divide that by the sample selected. Remember, we had 20 subgroups times 50 samples per subgroup. That's 1,000 pieces. The average fraction defective is 0.141. Keep that number in mind as we go along in our next bit of our calculations. Okay, we've progressed on our fraction defective control chart. You can see that we've completed our sampling here on the bottom. We've collected 20 subgroups of, if you recall, there were 50 little holes in the paddle. So sample size was 50 with 20 subgroups. That's 1,000 samples that we were selected. And that's sort of a nature of attribute sampling, is that the sampling typically is pretty cheap and quick, one of the advantages of attributes versus variables. We've calculated the average fraction defective just below it and plotted the points here on the chart. You can see that the first one is 0.16, and on the scale to the left, 0.15, just a bit over 0.15 is 0.16, and so forth. We've connected the dots, and we've calculated our average fraction defective. Let me show you what we did there. So the p-bar is the average fraction defective. And that's calculated a couple different ways, which way is easier for you. In our handout there, we've said that it's the total number of defects, and if you'll see that in one of the slides, there's 141 defects, and we again had 1,000 samples. That was 20 subgroups of 50 each. So the average fraction defective is 0.141. Another way to do that would be simply to add up all the average fraction defectives here and then divide by 20. You'll get the same number. So the p-bar is 0.141, and we have it noted here with the red line, and that should look symmetrical. About half the dots should be above and half below the average fraction defective. So in our next step, what we'd like to do is calculate the upper and lower control limits for the fraction defective to determine whether our process changes in control. And so our calculation for the upper control limit of p-bar is p-bar plus 3 times the square root of p-bar times 1 minus p-bar divided by n. Now you have to be careful there. N is not the number of subgroups, but it's the sample size, in our case 50. So if we plug in the numbers, p-bar 0.141 plus 3 times the square root of 0.141 times 1 minus 0.141 divided by 50. And if you make that calculation, we'll find that our upper control limit, well, why don't I go ahead and do that with you just so that we work together on it. Turn my calculator on. So the first thing to do is take 1 minus 0.1 minus 0.141, and that's 0.859. Multiply that by 0.141. That's 0.12119, 121,119. Divide that by 50. That's 0.00242238. We're going to take the square root of that. And that's 0.04921766798. So now we have this completed. We're going to multiply that by 3. And that's 0.147653 and so forth. And add that to 0.141. And so our upper control limit for the p-bar, the UCL p-bar, is 0.2886. Or we'll call that roughly 0.289. So So we found 0.289, just below the 30 there. And we can draw a horizontal line to indicate our upper control limit. And we see all the points are within the confines of the upper control limit. Let's go back and calculate the lower. If you calculate the lower control limit, formula for the lower control limit, the LCL, P bar, equals P bar minus the same thing here, 3 times the square root of P bar times 1 minus P bar divided by N. And if you do that calculation, you'll find that number is below 0, so we're not going to plot it. If you select a sample size that's larger than 50, say 100 or 200, you'll find that you will be able to calculate a lower control limit, which would say that it's unusual. You've made some, if you have points below the lower control limit, you've got statistical proof that, boy, the process really has changed. In our case here, we've estimated that the average fraction defective is 0.141, when we actually know that the average fraction defective in our bowl here was closer to 15%. So pretty good estimate. And we found that our sampling process, as noisy as it was in a state of statistical control. So there are several different types of tools you can use for measuring attributes. We talked about the fraction defective. There's also something called a C chart, and that is also useful in certain situations. It's called the number of defects per unit. Let's just say you're building some complex product and you want to monitor the quality of the overall assembly, and it has many different components, and you want to measure that. So you'll thoroughly tear down one assembly and count, maybe it's got a blemish here and a scratch there. This component doesn't work, so that's maybe 3. And you'll want to plot that. You want to make sure that the process, while maybe 3 is not acceptable, but it's at least consistent. You don't want it to get to 30. And a U chart is the number of defects per subgroup, similar to the C chart, but it's a bigger scale. Point is, there's more than one tool in your fraction or your attribute control chart toolbox. So, what applications will you use statistical process control on first? Where are the greatest quality costs? Where are you running into trouble first or greatest? Where is the most money being spent or lost? Which customer is complaining the most, and which process should you attack first? That's what you'll want to understand and decide as a team which application of statistical process control you'll want to jump on bandwagon first, get your feet wet, and enjoy the ride. So special thanks in creating this video for the use of So Many Fast video and the SPC training tools of the Suter Company in Sycamore, Illinois. Thank you very much. Well, you can learn about statistical process control in a lot of different ways. The references that I have pictured here are the ones that I learned from most. That is Duran and Greina's Quality Planning and Analysis. That's the book here with the sort of blue cover. Statistical Quality Control by Eugene Grant and Richard Leavenworth. The Statistical Quality Control Handbook, written by one with the beat up cover here, written by employees of Western Electric. Of course, Duran's Quality Handbook, which is a terrific reference for many things, and it has statistical process control well within it as well. The concept of the loss function comes to me from offline quality control, Genichi Taguchi and Yu and Wu from the Central Japan Quality Association, and of course the ASTM tables for control charts come from the ASTM. So thank you very much for your time, and good luck identifying and controlling variation with statistical process control. If you have any questions, feel free to reach me at the email. The next two slides are simply some blank forms that I promised you early in the presentation.